and I don't have to either worry about cutting out 10 minutes of extra video or. All right, so we have homework due tonight, right? So that's your homework for. Hopefully you were aware of this. But anybody have any questions or issues or anything like that with the assignment? Hopefully it makes sense again. And I hate to sound like a broken record for all of you, but sometimes some people don't quite catch when things are due. So um, hopefully straightforward questions for you, but mostly planning, get that all up into your GitHub accounts so that I can review them. But other than that, end of the day, yes, midnight. Notes, please. Go over here. Alrighty. Yeah, and we just to plan, right? So we have about 1 month left. So April has started. Classes are winding down towards the end. So try to plan appropriately. And again, if you haven't finished the assignment, we're looking for a minimum viable product, which is basically a working prototype or a demo that can demonstrate what you are building. It doesn't have to be polished, but it should at least do what you say it's going to do. It doesn't have to be pretty. To give you an idea, maybe of what I'm talking about, since minimum viable product is not always something. I started playing around with another P5 project since this tickles my fancy to do stuff like this. And this isn't done by any means. We've got some chunking, we've got some angry students following me around, but it works. I can demonstrate noise functions and sprites and simple artificial intelligence and a little bit of generative text. So I obviously you have no idea what this is. I've never talked about it. I try to avoid talking about projects because then I stop working on them for some reason. But yeah, I can actually demonstrate something working, which is, you know, kind of the goal with a project. So let's finish up UML here, and then hopefully you'll get into design patterns, and you can all go forth and become the best. So when we did the requirements in this, yes. So Mikkel, that's going to be your final deliverable. Your your final write-up for the project is going to be the software requirements spec or the SRS, where the requirements assignment you did is going to be the bulk of it. You're also, I keep forgetting to mention this, and it's probably good to know sooner rather than later. One other thing you will have to do are test cases for your projects as well. That's something that we will be coming towards when we do unit testing and test-driven development later on. But you can start thinking of how you're going to test your applications as well. And you're going to link them to your requirements too. And just so that I'm not freaking anybody out with this, um, I know that you are all doing things in different languages. I'm not expecting you to necessarily learn the testing frameworks for each of them. Tests can be manually done, right? You don't have to write a test runner. You don't have to write JUnit tests. You don't have to write, I know there's Unity tests. You don't have to do that. We can just manually prove it out. Like your test cases, I click new game, the new game, the game starts. Check mark. We'll get to that, but I just want to kind of clarify that for you all. And the reason why I bring that up is last semester I had people doing RPG Maker games, I had people doing Raspberry Pi projects that weren't really coding specific. So it's possible to test pretty much anything, but that's going to be part of your final spec. And bonus to you all, you already did half of it because you did the requirements assignment. So good job. All right, so we left off here with sequence diagrams, right? Did these make sense, more or less? So we start at the top left, and you kind of just follow the arrows as you go. And if you don't see a return arrow, there is some kind of an implied return. Things on the top are either going to be entities, so we have actors, or we have classes with instantiations, or anonymous classes. We have execution windows where this object is alive, function calls, constraints or guards. Hopefully pretty straightforward to kind of parse through. And if you're not, it will take some practice to get the proper feeling of this, but you should at least be able to read it, I would hope. So we left off here with the process, and what we're going to do next is we're going to talk about the other side of things. So sequence diagrams are one of our behavioral diagrams, right? We're showing behaviors, we're showing timing. Another type that we can use is the communication diagram. Also is called the collaboration diagram. Basically, we are showing the same thing as a sequence diagram. And actually, you might notice here, sequence and communication diagrams are semantically equivalent. And semantically, this is a very specific word, I probably should have bolded it. This is the intent of something, right? It's the meaning behind a word, is its semantics. If it was syntax, that would be how we construct it, right? To take that and apply it to like English, that's your adjectives, your nouns, your verbs, that's the syntax. But the meaning behind a sentence, that's the semantics. And as a aside, semantics are very, very difficult to do programmatically if you want to understand the meaning behind words. There's a lot of research down that path. But communication diagrams. Basically here we are trying to really get a feel for which object is communicating with which object at which point in time. Again, the idea is going to be the same with sequence diagrams, but we have a different perspective, a different syntax here. So instead of like these vertical lifelines, we basically see a flow graph here. And really the goal here is to show relationships, show dependencies. And these diagrams specifically are going to be numbered as well. So you can actually see what step is happening when, very, very specifically. So here we have a interaction with a librarian, and we want to see, go through our system and see if somebody can borrow a book, if they have any unpaid dues or unpaid fines, and kind of go through that process here. So librarian entity, still stick figure. We're going to go this direction. And you can do an arrow like this, or you can put the arrow right on the graph. They both work. We're going to call a function, inquire about a borrower. Well, if we have an invalid borrower, display that message, or check how many books they can borrow. Then, or sorry, this is part of this loop. This is laid out badly. If we basically don't know this person, go into this feedback loop here. If we know the person, how many books can they borrow? Okay, well, do they have any books checked out? Is there anything overdue? If there's something overdue, create a fine, return the fine amount to the UI, and then that's going to be no, return to the librarian saying, hey, you have a fine you have to pay before you can buy any more, or borrow any more books. Again, I could represent every single thing that you see here in a sequence diagram, and it would mean exactly the same thing. The difference is the purpose of the diagram. So here we are showing dependencies very, very clearly. We are showing steps very, very clearly. We still have function calls, which direct the flow of messages. We still have kind of return values and all that, but here we just have a different outlook. So here's our make appointment use case. It's actually a lot cleaner looking too, right? It's a lot less complicated. Well, we have our patient, we have our receptionist. Here we have just one line though. So again, if I want to request an appointment, go through the whole process, come back to the patient at the end. Do you want a new appointment, cancel, or change? Here are the appointment times. What we kind of see here is a figure that looks a little bit less cluttered, but we can have more things going on a particular path or a particular interaction, right? So here we have three actions, three activities happening between the patient and the receptionist. Whereas here, if we go back, we still see those three, but they're broken out, with a lot more kind of space. There's a lot more going on in this diagram. And there's no specific like orderings that you're seeing here. So really it's, to me, at least, they both show the same thing. So again, semantic equivalence. But it's just which diagram do you prefer using? What can you use to communicate your intent? They're both fine, right? They're both going to be pretty much the exact same figure. Just kind of depends on which particular diagram you like using, maybe which one your boss likes using or your company likes using. Maybe you want to show more interactions, more dependencies rather than the flow. This is a good diagram for that. So if we're going to build these diagrams out, let's set the context. And again, context is important because that's what we are doing, right? This whole thing here is the context. Here we are buying an online book. Here we are making an appointment. Here we are checking out a library book. This is the context. Then figure out what the objects, actors, and relationships are, or associations are between them. Pretty clear so far, right? These are the classes that we have. These are the objects instantiated from the class diagram. Let's lay them out visually, connect them as appropriate, figure out which function is being called when, and that's your communication diagram. Last step, which is important, and I hopefully mentioned it last time too, but we have to validate the models as well. And what validating is doing is you're basically sitting down in either a formal or an informal setting and walk through the model, right? Does this process make sense? You can call a formal meeting, you can do an informal rubber duck debugging session where you walk through this model. So I am a patient. I've got my two little friends here. I've got a patient. I've got a receptionist. Patient comes in, I need a meeting. Professor is totally not losing his mind, I promise. Walk through the model. I need a new appointment. You already have an appointment. Okay, let's change the time. This is going to go into a very weird place, so let's put the dolls down. But hopefully the idea makes sense. And with this idea of validation, you're going to apply this to any model, apply it to any artifacts that you have in your system. All right, so those requirement specs, we validate it, right? You walk through, you make sure you don't have any duplicates, you make sure the language is clear and concise and that it makes sense. You're validating your requirements. We're going to add test cases soon. What are test cases but making sure that your system is behaving as expected? So we're going to write test cases that validate out our software. We're going to link our test cases back to our requirements, because if we don't have a validation of a requirement, then how do we know that it was implemented correctly? And this all kind of links up together. So this set of slides, we have class diagrams, object diagrams, sequence diagrams, and communication diagrams. Anybody have any questions on any of these? Or does it all, short of getting practice with building them, does it all make sense so far? Because if we are good, we can move on. And if we have questions, I would much rather answer them now rather than mark you down because you didn't get something. Let me make sure I also have Discord open over here. Okay. Good. All right. So if we're good then, let's move on to design patterns. So has anybody ever used or anybody ever use a design pattern? Does anybody know what design patterns are? Any prior history with these at all? Or did we all switch off once he brought the dolls out? Not me. Fair point. Yeah, we could just do an entire class as like what is that VR chat or something like that? Hmm. I wish I could say these were my kids, but these are mine. All right. So a design pattern is something that is absolutely worth learning. And as you get deeper and deeper into programming, you are going to find that you're going to have reasons for using specific design patterns. And what they do is they save you time and they save you effort. Effectively, what they are is just a well-known construct that you're going to apply to a programming task, right? If you have, let's say that you're building a, oh, we can go back to my interesting little game demo here, which I find interesting, and I'm pretty sure that I'm the only one that finds interesting. But that's perfectly fine because life is just a bunch of hobbies. So I've got a little game here, right? And this beautiful background that you see is all randomly generated. And it's generated via something called simplex noise. So this is a noise function. I could swap this function out, or this algorithm out, with another one. Maybe I want to use marching cubes. Maybe I want to use whirly noise. Maybe I just want to do a cave generation type of thing. Kind of the point is that, if I were to want to swap out an algorithm, I would use a particular design pattern for that. So there is something called the strategy pattern, which exists for literally swapping out algorithms at runtime. If I want to, say, provide a nice interface for developers to access my service, so let's say that I'm building a web application, I've got a bunch of stuff happening behind the scenes, but I don't want the developers to know that. I just want them to call an API. Well, maybe I'll build them an interface. Or, there's a couple of other ones too. There's facade as well. Basically, there are a lot of well-known programming issues that have been solved by design patterns. And what this does is it describes to you exactly what you need to do in a particular situation. And as a spoiler, these are kind of designed around object-oriented programming because they're going to take advantage of things like overloading and classes and inheritance and polymorphism and all those things that you probably touched on in Java 1. But there is absolutely nothing stopping you from doing this in C or C++ or Ruby or Python, right? If you're going Python, I mean, you do have object-oriented programming. I'm going to show a lot of examples in Python because I like Python over Java. But if you were to do a lot of this in C, we don't have classes in C, right? Well, no, but we have function pointers, and we can kind of do really tricky things under the hood to make these work. So yeah, basically we have these well-known patterns, and we have creational, structural, behavioral types. We'll be going over all of these. But one of the other things which is also kind of worth talking about, and I don't think we're going to talk about this until the end. I've got like 3 or 4 sets of slides on design patterns. There's also anti-patterns, which are examples of design patterns that you should not apply. It might make sense to apply them, but they're actually worse than if you had just done something brute forced. Example of that would be, well, there's something called the God class. So if you're, a new Java developer, um, you think, let's just keep everything inside one single class file. It's going to be responsible for everything. We're going to spawn the GUI from here. We'll talk to the database from this class. We'll do all of our algorithms from this class. Everything's in one single class file. Okay, well, it's easy for you to parse out and read, but it just becomes a horrible tangled mess. And I guess with anti-patterns, we can also get into the term technical debt, which we will talk about at some point, but that's a very hot buzzword in software industry right now. But let's get into this. So if you have ever seen this textbook, and if you ever see it for cheap or free, I really like this book. I actually made a PhD student take an exam on the topics inside because he needed a background on design patterns. It is a great book, and I'm not saying go out and buy it, but if you're interested in design patterns, it's worth having on your shelf. So what a design pattern does is it abstracts, I'm just going to stick with part of this. It abstracts out what you need to do for a particular problem. So in software engineering and software development in general, what you're going to find as you go is you're going to be doing a lot of the same things over and over and over again, right? And I'm not talking about, your intro to Java programs where you create a RPN calculator or you build a GUI interface, kind of basic thing. I'm talking about like, how do we swap out algorithms? How do we provide a interface where we hide the details? How do we reconfigure our system? These are all problems which are kind of high level, but they can be really applied to very specific areas. So it's reusable, which is great. So we have proven solutions. And what we mean by proven, rather than ask you and wait for an answer, let's go right into it. Proven means that time and time again, these solutions have been deemed to be appropriate and good for the problems at hand. Basically, we have a lot of empirical evidence, and empirical meaning that we have seen it over time, that these things work. So a few kind of high level things here. So why study them, right? So one of the best things that you can do in software engineering is to reuse code and reuse ideas, right? If you are starting from scratch every single time, a project is going to take you forever. But if you learn along the way, and you start reusing things, reusing ideas, it takes you a lot less time to get things done. And I'm not saying, copy and paste old code, but if you understand how a particular bit of code works, you can reapply it in a new context. And that's a whole other field of software engineering where if you take legacy code and you just plop it in, that can be problematic. But let me go back to my little game example here. I wasn't planning on talking about this honestly at all, but this demo here, right? So this map, and I've got a bunch of little worlds here. Disney reskins their animation. Yeah, that's the Xerox era, probably still going on, right? But this little P5JS demo here, it probably took me a solid day to 2 days to code, which I did this in Godot last semester, and it took me weeks. And I did it in Unity the semester before, and it took me still weeks. Kind of the idea here is that I know exactly what I want to show. I'm reusing the ideas. I'm doing it in a different language, right? Godot is kind of like Python plus their interface. This is pure JavaScript. I already knew what I had to do, and I knew exactly which patterns I had to apply. Like, for instance, this map that you're seeing here, this is just a 2D array of noise values. And if the noise is less than 0, draw some ground. If the noise is less than 0.2, draw some water. If the noise is less than 0.4, draw some trees. Well, how do we grab random trees? Well, we have this sprite sheet, which I can just grab random entities out and plop it into my figure here. Again, reuse is a great thing if you can kind of, keep ideas in your head, or at least written down. All right, so other things we can use design patterns for is that it helps with communication. And what communication means in this context is that your team will understand what you're doing. And even future you might understand, right? Because as programmers, we comment and we write down ideas so that, the me at 3 in the morning writing code can tell the 8 a.m. me what he did in a horrible long night of coding type of brain. But if I tell all of you to go and implement a singleton, obviously you might not know that now, but you know exactly what I will be talking about, if you learn what that pattern is. Singleton means we only ever can have one instance of a particular object. So it helps with learning, it helps with communication, and it helps with reuse, basically. And we know that these patterns are proven to work. There's an interesting idea, though, that sometimes design patterns kind of migrate over to become anti-patterns. So this is where something that works right now in 2021, maybe in 2022, we find that was a crap idea. Let's not use that anymore. And an example of that, just because I'm in the roguelike mood, there is a design pattern called Entity Component Systems, or ECs or ECS. That's where every single thing on your game or your graphics project or whatever project you're building is an entity. An entity has an update function, an entity has a draw function. Basically, we are abstracting all of the control to every object, right? This cup of coffee has an update function. This moss of water, or giant mug of water, has an update function and a draw function and a professor drink me because you need more caffeine function. This was for a while a great idea for games. And what I'm starting to read in some various blogs and various forums that people really are starting to not like this design pattern anymore. Because people are starting to apply it to things like user interfaces and things where it doesn't make sense. So I've seen arguments that a well-known design pattern is now becoming an anti-pattern. So just kind of one of those things where you kind of have to keep up with industry and keep up with what's going on because what you know now might change in 2 years or something like that. Anyway, so this is going to help us out. How we're going to enable these patterns, we're basically going to leverage object-oriented design. Now, again, we can do this in very procedural languages. If you're going the functional route like Lisp or Racket, then you're on your own because I am absolutely terrible at those. But we're going to be using things like encapsulation, like polymorphism, information hiding, interfaces, compositions, basically where we start being able to really tag and specify various properties, again, based on this whole object-oriented notion. That's where all of these design patterns come from. And if you have no idea what the heck I'm talking about, think of your classes that you build in Java, right? We have the variable aspect where they're, public int ID or private or protected, right? Those little designators are going to become very important for us in this area. Same with, extends and imports and, all of those kind of object-oriented ways of bringing in functionalities. We're going to really leverage those here. Okay, so how do we describe design pattern? I promise we'll get to at least one today. The reason why we're going through all this kind of basic rigmarole is so that you really understand that there is a very specific way we talk about design patterns. All right, so we have a pattern name and we give it a classification. So is it structural? Is it creational? Is it behavioral? What is the purpose of this design pattern? So let me pop all these up here. And if you decide to go into software engineering research, one of the areas which you could go into is figuring out new design patterns, figuring out what is a design pattern and what is an anti-pattern. There are researchers who solely look for that. They might do it in new languages or they might go back to old languages and verify, but this is a legitimate area. And it's something you'll use in industry, you'll use it in home projects, you'll use it in school. So it's definitely worth picking up. So we need, for a pattern, we need the intent. So what is the problem we're addressing, right? If I don't have a problem, why do I need a pattern for it? What's the structure of the design pattern? So this is where we can use our UML knowledge, provide a UML diagram of how this pattern actually looks, right? When we talk about the singleton, that's just one instance of a class in memory. Like you can only instantiate this class once and never again. We can copy it, but we can't reinstantiate a new, area in memory of that. What's the structure of this diagram? Well, let's show a class diagram, maybe with a associated object, or we'll show an object diagram, but we'll only ever allow one instance of this class. Okay. So we'll also show participants. So who is participating in the pattern? So which classes? What are their responsibilities? What are they supposed to be doing here? Are there going to be any collaborations or interactions between classes? Are there any consequences? So if I use pattern A, what is going to happen? Are we going to absolutely blow out our available memory? Are we going to be limited to one instance of a class? Is it just hard as hell to implement, but it's actually going to save us a lot of time in the long run? Just kind of depends, right? And some of these can be UML, some of these can be like prose or written language as well. Then provide an implementation. So here is some sample code. Here are some, hints to get going. Maybe here are some common problems that people have experienced when trying to implement this pattern. So these bolded lines, line items that you see here, these are basically just, templates, column headers that would be filled out for each design pattern, as well as sample code. Forgot one. All right, so to give you a bit more history before we start moving on to them, originally there were 4 people who did the early work on design patterns, so basically figuring out how we can describe these, realizing that these things actually exist, right? All they really did was look at all these software projects and realize, hey, there's a lot of overlap in some of these strategies. Let's catalog them. That could be great for people who maybe don't understand or don't know that this problem that they're trying to solve is not new. Here's a solution that's already well known, right? So they come up with this idea, they describe a way to catalog them. So basically they come up with this list here. And then they figure out 23 patterns. So the initial set of patterns that were discovered, there's 23 of them. Now these people here, and these are software engineering researchers, they didn't create the patterns, right? They didn't spend years of their lives coming up with 23 brand new solutions. They just looked at what already was out there, right? So let's look at open source projects. Let's look at industry projects. Well, it turns out that when we make let's make an API, we're probably using a facade pattern. Probably wasn't called facade until they sat down and modeled it out and looked at the structure and like, hey, this is a facade. So basically we have this idea. And we have 3 categories. So there's creational, there's structural, and there's behavioral. Behavioral and structural, very similar to what we talked about with class diagrams and with sequence diagrams, right? This is the structure of a program. This is the static aspects. These are the dynamic aspects. These are the interactions. These are things that are being expressed at runtime. Creational is basically like the underpinnings of our programs. So it's how we build them up. We'll talk about Singleton from creational. We'll talk about facade from structural and observer from behavioral. And I will have you implement a pattern later on just to get you prepared for that. If I was mean, I would make you do observer. I'm trying to remember which one I made them do last semester. I was actually quite nice about it. Observer can be a royal pain in the butt to implement. But on the plus side, before anybody starts freaking out or getting worried, by being design patterns, these are well-documented things with code examples all over the internet. So let's start with creational. So creational, what they give us is a way to really help out with instantiating objects. So we are creating things, instantiating classes. We are instantiating things in memory. That's where creational gets us. Structural, again, that's the static aspects of our system. Behavioral, dynamic aspects of your system. How things work together, how they interact, how messages are passed. How can we abstract these classes of problems into well-known solutions? So let's jump right into creational. So we have the Singleton pattern. Any of you ever hear of Singleton? I keep looking at the chat and seeing Disney reskins their animations, and I just get a kick out of watching like the Robin Hood movie and Aristocats and all those ones where you can kind of see the lines that they didn't fill in because they Xeroxed the animation cells. Right. So, framed in the idea of singleton versus event systems in Unity. Yeah, I have to confess I do not I know enough about Unity to know what you're talking about. I don't necessarily understand like the deep underside of the event system, but yeah, like I can play with Unity, I can build fun projects, but I haven't given it enough time. And God, I've been trying to learn Unity for like 5 years now. I give it half a semester of effort, and hey, you're doing code reuse, so that works fine. Nothing wrong with that. All right, so let's talk about singletons. Singletons are a type of creational pattern where, like I said, you only ever want one instance of this class in memory. Okay, so we are not playing Four Swords Adventures, we are playing Original Legend of Zelda. There's only ever one Link, okay? There's only ever one instance of that. So if I were to say, let's create a class, let's get away from the dolls, let's call it class whiteboard marker. If I instantiate this in memory, I have a reference to a memory location, right? It references this marker. If I instantiate it again, depending on your implementation, either you're going to throw an error because we can only ever have one, or all the copies of this marker, let's grab some more here. I realize they're not all black markers, but just pretend. So I've got multiple markers now. They all point to the exact same location in memory, right? So we only ever have one memory space for an object, a specific object. Now, the intent of this is to provide a global point of access for it, right? And the point is to have one thing that we can reference in memory. So how do we implement this? Well, we're going to make the class responsible for instantiating itself, and the class is also responsible for knowing if it's already existing in memory or not. Okay, so we have just one instance of a class. Any idea why that would be useful? So why would we only ever want one class? Is there any purpose to this? Global variable storage in a program. Yeah, that's one of them, sure. So we can use it as a dumping ground for storage. That I've seen that before. Where I most commonly encounter singletons is with random number generators. So this is kind of a good example. Let's say that you're writing a program where you're taking advantage of random, right? So you're calling math.random, or you're calling, getting random integers or random floats or something like that. If I call random, I'm drawing numbers from a distribution of numbers, right? So basically, I'm not expecting you to understand random number distribution, all that fun stuff, but when I start using random numbers in a program, they're not really random, right? They're pseudo-random, meaning that I'm going to generate a massive list of numbers that I can pick from. And if I know what, say, the seed value of that number generator is, I can replicate this exact random number every time I run the program. So I know, the majority of you probably have played a video game before, right? And a lot of you probably have played Minecraft. I play The Binding of Isaac from time to time, or Terraria, or any of these games where there's inherent randomness. Well, you probably also know that you can put in a seed, right? And you get the same game every time. That's because we are probably implementing the random number generator as a singleton. And if we do that, there is only ever one distribution of random numbers for a particular seed. If I store it as a singleton, I can ensure that my game is going to be the same every time when I put a seed value in. Or if we don't seed it, we will just be truly, random-ish. But we can tell the user what the seed value is if they want to say share it with their friends or go back and play it again, or if we want to go in and do deep testing on a particular thing that we generated. So basically, singleton, we can ensure that there's only one ever instance of that. And kind of why I'm talking about this random number generation thing, you can have multiple random number generators, say in games or in simulations, but there is no way to guarantee that we will ever get that behavior again without a massive amount of headache, keeping track of seeds. But if we make a random number generator one object, which we can never reinstantiate and we can basically never blow away, well, we have guaranteed behavior. RNG is one of them. Okay, global variable storage, like you say, is another one. Now, last semester, somebody asked me a very good question, and it was actually related to your point about variable storage. Can these change? And there is actually a debate on the internet and between software engineering people that I know about that point. So if I instantiate a singleton, can that ever change? Like if you are making global variable storage, can I update a global variable in it? And the answer kind of depends on what you want to do with it. Technically, yes, you can update things inside a singleton, right? If you are, let's say we're building a game and you have the width and the height of the screen and you store it off into a singleton, well, what if the user wants to change their resolution? So we go from 1024 by 768 to, full screen, whatever the resolution of your monitor is. Can you update that singleton? Sure. But if you are creating a singleton, there's a good chance you have made things static inside of it. So you just basically have to give the user the ability to update things. Maybe have like a get and a set feature of your singleton class. Excuse me for once. All right, we're back. So how do we implement a singleton? That's the why of it. And again, all of these patterns are thinking about common problems and how do we solve them. The implementation's just the mechanics. That's the easy part. So we're going to add a private static member to reference the desired object. So initially it's going to be null. So let me pop all of these in. We are then going to add a public static method to instantiate the class if this private static member is null. If it is not null, or I guess after we instantiate it, we're going to return that member value. So depending on your implementation, what this means is that if I call singleton.new, there will be a private member of singleton class referencing the instance in memory. If it is null, create a new one. If it is not null, return that member. All right, and then we're going to set the constructor of this singleton class to be either private or protected, meaning that nobody else can instantiate it. So this is where, when I talked about using those object-oriented features, so here you see private static, public static, private protected. These are all object-oriented features where we can basically implement data hiding, and we can control access to our classes. So what are the consequences here? Well, we have controlled access to a sole instance, meaning that we have very specific ways that we can access the singleton. We can very easily adapt this too. So maybe we want more than one fixed instance. Basically what we're seeing here is what's going to happen if we implement the singleton. And I have this access controlled subclasses in bold here. Basically, if we make something protected instead of private, subclasses of a parent class can still access those variables in those function calls. If it was private, only the class itself could access it. Protected child classes can access it. We'll get into private and public and protected just as a refresher in case we forgot. But basically, what we have here is a way to protect ourselves. And this is a lot of wording for showing you something that actually looks like this. So here's our UML. We have a singleton class. We have a private singleton variable. We have a private or protected singleton constructor. And then we have a public call to get instance. Okay? So when I said UML is going to be helpful, here's hopefully why it's helpful. You can very easily see, okay, so we have public class singleton, we have private singleton, private singleton, public get instance, return this dot singleton. By constructing a class like this, you can only ever have one instance. And I should say there's obviously the code that we have to write too. I'm not going to do the Java here. Some of them I will. Some of them I will refuse to do. I have no problem saying I'm not a big fan of Java, but we'll do some. You'll see me kind of struggle with Java when we get to unit testing because we'll play with JUnit and fun stuff like that. But here we have a class singleton. Here's our private static singleton instance. Here's our constructor, and here is our call to get instance. So the way this is working here is that if we call get instance, if our member here is null, well, let's create a new one. And this is the only way that this class can be referenced, right? So if I am building a public class video game, for example, and video game is going to create a random number generator, well, I would wrap my random number generator in a singleton class. And if I ever wanted an instance of my random number generator, I would call rng.getInstance. That way I can ensure that there's only ever one copy of this in memory. We can also make this protected as well. Again, so if we have child classes, maybe we want to have the ability to call this. But where are we at here? 948. Let me show you the example in Python because I want to spend some time talking about this next time, private and protected. But let's take a peek at a Python. Okay, so here we have some Python code, and this is basically the Pythonic way of writing that Java class that I just showed you. So in Python, we can have classes. Here's my instance, and it's double underscore to pretend that it's private. Here's a call to get instance. We have an initialization function, and I have some calls to singleton. All right, so I want to call the singleton class, and I'm just going to print it out, and I'm going to call it multiple times here. All right, so let me actually do this. Let's do a double singleton. A tmux screen going. All right, so Python singleton. Actually, now we can't see anything. All right, there we go. So what I'm doing here, and let me really quickly change my font size to, let's go 18. It's a little bit better. So on the right here, I ran this code. I see singleton object and I see the memory address. We see that this memory address is identical every single time, meaning there is only one instance of this class in memory. Right, and I'm just kind of hand waving the Python code here because, again, it's something that we should be able to learn how to implement if you want to go through with learning this. But we're implementing the UML diagram here, right? Let's instantiate a singleton and print it out. If you print a class in Python, it just prints out this is an object at this memory address. Well, let's call getInstance. Print that out. Call getInstance. Print that out. So I've got three separate variables, right? They're the same variable name. I could call this S1 and S2, and I'd get the same thing, right? So the same memory address here. Basically, I've implemented the singleton pattern, and I could use that for whatever my program needs now. All right, I don't want to keep you any later than I already have, so last minute questions. Otherwise, the stream is over.